In this video, we're going to repeat our eigenvector calculations, but this time with a 3x3 matrix to see how that works. We're going to reuse the 3x3 matrix from earlier, where we had computed the eigenvalues of 2, 3, and 4. Our first step is to remember the eigenvector condition. And the eigenvector condition requires that this combined matrix, A minus lambda I, times a vector v has to equal the 0 vector, and our v vector that we want has to be non-zero. All right, well, let's work through our lambdas in numerical order here. We'll start with 2. So if lambda 1 is 2, we're going to use that in this equation. So this is b minus lambda I for this particular instance here. We're going to have b minus lambda I times a vector equals the 0 vector. That's the same thing as saying our 3, 1, minus 1, 0, 2, 5, 0, 0, 4, minus 2 down the diagonals. All of that multiplied by something, by our vector v. Well, let's define that vector v as a, b, and c. Just 3 values we don't know, 3 unknowns, 3 scalars. And that has to equal the 0, 0, 0 vector when we're done. We'll do a quick tidy here. 3 minus 2 is 1, 1 minus 1, 0, 0, 5, 0, 0, and 2 times our ABCs equals the 0 vector. And we get our check right away that this is not invertible. This matrix here, we can see that these two rows here are multiples of each other, and so we'd be able to cancel out one row completely with row operations. All right, well, how does this help us solve? We get from the first line that a plus b minus c has to equal 0. And let's take the simpler of the two lines down here. We also know that 2c equals 0. So we get one of these ones for free. C has to be 0 to satisfy the set of equations. That still leaves a and b in play, though. So let's sub that into here. And we're going to find that a plus b, without the c's now, has to be 0. A is equal to minus b. And actually, that's good enough. Now we just have to pick a value. Let's pick b equals 1. And that will lead to then a being negative 1. With all of that together, we're going to get a final new vector, v1, as negative 1, 1, 0. Like so. And that is our first eigenvector for our first eigenvalue. Any vector in this direction will be scaled by 2 by the matrix B here. Lambda 2 is 3. And reminding us what we're doing, b minus lambda I times v is the 0 vector. So we copy our matrix down, 3, 1, minus 1, 0, 2, 5. There will be a change, of course, though, because now we're subtracting down the diagonal again, but we're subtracting 3 down the diagonal throughout. Our v is some unknown vector. We're going to give it components. And our 0 vector is just the 0 vector. Then we tidy that up. We actually express this out. We get 0, 1, negative 1, 0, negative 1, 5, 0, 0, 1 times a, b, c equals the 0 vector. And right away, we can see that this is not invertible. This column of zeros would give a determinant of 0. And again, we want that. That's our check. So working with this, so how do we actually get the values out of this? Well, we have these two equations could be canceled out. Let's start with the last one. The last one is c equals 0. And if c equals 0, we also have minus b plus 5c equals 0. Well, that's 0, so b has to be equal to 0. That's 2 of the coefficients. What about the third? All we know is that 0 times A plus some B's and C's, B and C are 0, or 0's. Well, this can be counterintuitive. A can be anything. B, anything. And again, this feels weird at first, but if the coefficient is 0, I can make A 10, and it'll satisfy this equation. It'll have 0 times 10 is 0, that's fine. A can be 1,000,000. Oh wait, this is how we picked things before. We could have done that in the earlier examples. So we're going to pick a simple value for A. Let's just pick 1. And that's going to give us our second eigenvector to go with our second eigenvalue. And that's going to be A is 1, B is 0, C is 0. So one of the basis vectors here, if we multiply B by this, we're going to get 3 times that vector back. Hoo-wee. All right, let's fold that up here and keep that with the matching corresponding eigenvalue rather, and do the third eigenvalue now. It was 4. We're building our B minus lambda I. I'm repeating this because you got to do this practice to ingrain that construction. Our B minus lambda I times V equals 0. Copy our matrix in. 3, 1, minus 1, 0, 2, 5, 0, 2, 5, 0, 0, 4. Down the diagonal, though, we are now going to subtract 4. We're going to take that matrix, we're going to multiply it by ABC, and we should get the 0 vector back. That matrix can be represented instead, just doing the calculation. 0, minus 2, 5, and 0, 0. Oh, there we go. There's our obvious not invertible matrix. Check. Not invertible. Good. We can do our RAF. I'm just going to do it longhand here. Let's write this out as minus A plus B minus C equals 0, and minus 2B plus 5C equals 0. And the last equation, the 0 equals 0 already. This second equation is simpler, so let's make that, bring this over, we're going to get a double negative. So I'll have 2b equals 5c, or b equals 5 halves of c. So looking at that, I'm like, let's pick a nice value that's going to work out with integers here. Let's pick c as 2, and we're going to get cancellations happening. That's going to give us b equals 5. And then this last equation here, or the first equation here, is going to give us minus a is minus b plus c, or a is plus b minus c, there we go. And plus b is 5, minus 2 for c, that's going to be 3. So a is 3. Pulling that all together, we get our vector. v3 is the a, which is 3, the b, which is 5, and the c, which is 2. And I would argue no one looking at this matrix, without having done all these calculations, would recognize that this vector, or multiples of it, are just scaled by 4. If you multiply this vector by b, you're going to get 4 times that vector back. You can check it if you like. Now to close off, we'd like to summarize the effect that b has as a linear transform. Looking at this matrix again, to the naked eye, it's not obvious what these 9 numbers mean altogether. However, we found that we can summarize it quite nicely. Looking back at this first calculation, any vector along the direction of negative 1, 1, 0 will be scaled by a factor of 2. So it scales v1, negative 1, 1, 0 by 2. It also scales v2, which was our very simple direction. It was just 1, 0, 0 by 3, and the transformation b is a linear transformation, scales our third vector v3, which was this more complicated 3, 5, 2 vector, by 4. And I want to be explicit here. Just move these over for a second. and give them their correct names, which are the lambda values or the eigenvalues. So we can characterize the matrix B by the 3 eigenvectors here and their scaling factors that B would trigger in them if we applied B as a transform.